Welcome back to section 21.1 through 21.2. In this video, we'll be going over the principle of impulse momentum and how it looks for three-dimensional problems. We'll be looking at the derivation of angular momentum and where the inertia tensor came from. And then we'll be applying those equations to example 3 to find its momentum about a point O. Alright, so let's revisit impulse and momentum, the principle of impulse momentum. So we'll start off with linear. So if you remember, linear impulse and momentum was just mass velocity plus impulse equals mass velocity. This applies the same stuff that we did with planar. It looks the same, except now we just have a vector in 3 dimensions instead of 2. So mass velocity of g, velocity of center of gravity at state 1, plus the summation of the impulse, so the forces that cause a change in velocity. So remember, these have to be in the right direction. Not all forces will cause a change in velocity. Mass, velocity, center of gravity at state 2. And then for angular momentum, so this is largely unchanged. Nothing really new to talk about here for 3D, except you just have 3D vectors. H naught, so this point could be this can be any point that you want. I'm just going to use O, but you could do G, you could do some arbitrary point A, whatever you want. And we're going to take the summations of the same moments. The important thing is that everything happens about the same point, so you do your moments about O as well. These moments will be a vector now. And H naught 2. Again, you can change that base point from O to some other point if you need to. So not too interested in moments. You did moments a whole bunch when you were in statics, so you should be able to find those, integrate those using your calculus skills. So the new stuff is going to be these H naught terms. And what do those look like? So our angular momentum, which is what H naught is, so we can find that. So recall that we had H naught equal to dmv for a particle, and this will kind of map down to all of this. So in the book, they're going to use rho, and I'll kind of show you the diagram here. I can bring it up. I believe I put it in here. Yeah, so there's this rho A, so really it's just a radius. So I'm going to use r, but it is not the same r as you see in the coordinate system here. Okay. But I'm going to use r just so you don't think that it's a density. But it is in the local coordinate system. So if it helps, you can say that it's the radius to O from our base point A, because again, we use the base point A for our local coordinate system a lot. We cross that with omega, that's a vector, cross with the same RO, and that O is in the A coordinate system. And then we're going to integrate that with respect to mass. So d, m, and then v. So omega cross r gives us our velocity. So dmv. So that's about some fixed point O. So this is for a fixed point. If I go about the center of mass, and if you want to see all the derivation details, they're in your book. It'll look the same. So I'll write that out and then come back. Okay. So about the center of gravity, we're going to say we're going to integrate with respect to mass. Our distance will be the distance 2g from our base point A, and omega, and then again 2g within our local coordinate system. And so if I want to find it about some arbitrary point, so instead of a fixed point or about a center of mass, those are the two most convenient. But if you needed to move it somewhere, then you would use basically parallel axis theorem to move this. So arbitrary point or any point. So I'm going to use P here just so we don't get our subscripts. You can also call it A or whatever you want. But I'm going to use P so we don't get it confused. So this is any point that we want. So this is going to be HG plus, and then the radius 2P from A. And we're going to cross that with our mass and our velocity of our center of gravity, where mass is a scalar. So this looks a lot like parallel axis theorem. And so if you take these equations, you can rework them so they're not integrals. So if you put them into rectangular components, so x, y, z coordinate systems, then what we get is the following. Hx will be Ixx omega x minus Ixy omega y minus Ixz omega z. And these omegas are in your local coordinate system. So again, kind of thinking like when we went back to kinematics, we found omega in the A coordinate system. Same kind of stuff here. And so Hy and Hz will look really similar, so I'll write those out and be right back. And there you go. So we have our mass moments of inertia, x, y, and z, by their respective omegas. So this is all we had when we did planar. We just had Izz, omega z, or whatever. But now we have three-dimensional bodies, so we add in our products of inertia. And then, so for instance, xy is omega y, and then xz is omega z. So you can kind of see the pattern here. And then hopefully you also picked up on the negative sign here. So remember I said there was that tensor that we wrote earlier. This thing. So remember we had these negative signs. I said they came from the derivation of momentum. Well, this is that derivation. So that's what the negative signs are. And again, if you look at the book, if you want to see the full, how you get from here to here. If we do a really good job and we are able to find our principal axes, so, we have our shape, and we're intelligent about, we put it in the center of gravity, and then we rotate it so that everything's symmetric, then our products of inertia will drop out to 0, and these will simplify out really nicely for us. So instead you'll get Hx equal to Ix omega x, Hy equal to Iy omega y, and Hz equal to Iz omega z. And that's if you can make your products of inertia go to 0. Okay? So let's apply these to example 3. Alright, so we've been asked to find h0 of a disk. We've been given that omega 1 is 10, radius per second, omega 2 is 5, and the mass is 15. So omega 1 is about the y-axis, and it's actually the opposite direction. So omega y is negative 10. And omega 2 is about the z-axis, and it is following the positive as it's defined. So I've drawn the coordinate systems they provided. So this means that our omega z is just 5. The mass of the disk is 15 kilograms. So we have been asked to find h0. So we know that h0 will take the form hx, hy, and hz. And all of these will be about 0.0. So that's our base point that we're going to use for our coordinate system. So we're not going to move our coordinate system around if we don't have to. So let's write these out. So hx has the form Ixx omega x minus IXY omega y minus IXZ omega z. So I have omega y, I have z. Omega x is 0, just so you know. So this term is going to zero out. And then if I look at xy and xz, so let's draw that real quick. Okay, so up here, let's draw, we have a circle. The circle is in the x and the z plane, and then z and the x gives us y pointed out. This should be in the center. I didn't quite get it in the center, so let's me kind of move it over. All right. If I draw this in the, let's go in the zy plane, then I have a rectangle that looks like this. And if I draw this in the, so I have what? xy. I need xy is the last one I need. So let's have y out here, x down here. It'll be a rectangle that looks like this. So that's kind of the three views. What you should notice is that in all cases I'm symmetric. So that means our product of inertia is 0. It's 0 in all cases. So this means that IXZ is 0, IYZ is 0, and IXY is 0, and the other pieces. Remember, IXY equals IYX. So any of these products are going to zero out, so I don't even need these products of inertia. So HX is 0. HY, so that'll be IYY, omega y, and then it'll be minus 0, minus 0, because again, I'm going to have a product of inertia in the XY, and a product of inertia in the ZY. And again, we've established that all of our products are 0. And I'll go ahead and write out HZ just so you can see it. IZZ, omega z, and we'll get some minus 0, minus zeros as well. For the same reason, our products will be 0. So I have no products of inertia. I've actually put the, again, that's the idea. If you can make you can find your principal axes, then you'll be in really good shape. Makes your problems a lot easier to solve. So all we need to do is find IYY, IZZ, omega y, and omega z, because I do have omega y and omega z found. So I know this and I know this. So I just need to find IYY and IZZ. So IYY, so this is the mass moment of inertia about the y-axis. So we're going to be looking at this diagram here. So it's going to be a circle. And for that, we're going to use, so circle about its center. If you look in the back of your book, it's 1/2 mr squared. So that should be equal to 1/2. The mass is 15. The radius of this disk, sorry, I didn't write that down. Let me get that for you. The radius is 150 mils, which is 0.15 meters. So 0.15 squared. And that'll come out to be, let's just write it down here, 0.1688. We don't need units right now. Okay. And then we need IZZ. So I can get that in this one. So Z is the axis of rotation in this one. It's the one that's not showing. So it's going to be, so it's still a disk. So don't go get like a rectangle or something. It's still a disk, and it's about its edge. And so if you look up the thing, you find that IX and IZ, because X is still in the showing. This is basically the same thing. So you go look up your disk, you're going to find that it is 1/4 mr squared for this case. So I'll go ahead and write that IX is the same thing, but we don't need IX because we established that it is zeroed out. Anyway, 1/4 mass radius squared. You plug in your numbers. 1/4, 15, 0.15 squared. So it should just be half of that number. And that is a 0.08438. All right. So then all I'm going to do is I'm going to say that, let's just good and Good. Just kind of making some organization here. All right. And good. So then all we need to do is find our things here. So we need to just plug in 0.1688. Omega y is a negative 10. And hz is a 0.08438. We're going to plug in a positive 5. We'll do all that calculation. We'll find out that h naught is a 0, a negative 1.688, and a 0.4219 after you calculate these numbers. So this will be for the y, this will be for the z. Alright, so again, just kind of recapping what we did. We had a disk. I didn't draw the other piece because it wasn't part of the problem. Like, it causes the rotation, but we don't have any masses or anything for it, so we can't analyze it anyway. We try to find h naught about the disk. We know that h naught is these pieces, so we wrote the equations for those three pieces. We established that our products of inertia for all views were 0. So for every single plane, we had no product of inertia. So whenever we did IXY or IXZ or IXY or IYZ, so on and forth, like all of these products of inertia. So we end up with just the simplified equations. Omega x was 0, because that's what we were given. We were given rotation about the x-axis. So we just had to find IYY and IZZ, and we just did that using stuff that you've done in previous sections. Did some algebra, and got to our answer. Oh yeah, the units on this are kilograms, meters squared per second. If you have any questions, feel free to reach out.